Welcome to this afternoon session with one of the talks celebrating an EMS prize 2020. My name is Javier Cabré, and it is a very big pleasure to introduce one of the awardees, Joaquim Serra. Joaquim Serra got his PhD at the Polytechnic University in Barcelona, 2014. After that, he held a postdoc position at the Weierstrass Institute in Berlin, and also a Swiss National Science Foundation position as Ambizione Fellow at the ETH Zurich. Currently, he's assistant professor of mathematics at the ETH, still in Zurich, where he holds an ERC starting grant. Among other prizes, besides the EMS prize, he got one of the most prestigious math prizes in Spain, the José Luis Rubio de Francia Prize 2018 from the Royal Spanish Mathematical Society. Regarding his research, he has provided very relevant contributions in three areas, and I cite pretty much chronologically his contributions. First, the regularity theory for integral differential equations, including fully nonlinear integral differential equations, but also new results, new striking results for the fractional Laplacians, such as the Bogosaev identity for the fractional Laplacian. Second area, the regularity of the so-called non-local minimal surfaces, a recent geometric theory, and contributions to the related field of fractional phase transitions, and the fractional, what we call the fractional de Giorgi conjecture. And finally, and more recently, the third area are free boundary problems, where he has contributed with very fine regularity results for the classical obstacle problem, as well as the Stefan problem. So, big pleasure to be the chairman. Go ahead, Joaquim.
So thanks a lot, Xavier, for the generous presentation. You forgot and intentionally or to mention that you were my PhD thesis, and I would my PhD thesis advisor, and I would like to say it, and I'm very indebted and happy about it. So I feel very honored for the opportunity to speak here, and in some sense, I would like to invite you to a journey through time and across different mathematical problems, from the theory of branching singularities in minimal surfaces and towards recent results on smoothness points in an ice-water interface, as we will see. And I will use this timeline chart to keep track of the different topics that will keep appearing, and very importantly, the connections between them that we will discover. So first topic is minimal and constant mean curvature surfaces. So in other words, these elegant shapes of soap films. And the questions here are these surfaces smooth? How do possible singularities look like, if there are any singularities? And how large can the set of singularities be? These are the basic questions we are interested in. And here, the key ideas of the, so I would say that nowadays the answers to these questions are very well understood. And a bit the key ideas, that led to this theory, I have selected 4 here that I believe they are very important. And on the first place is the Lagrange, the Lagrange PDE, so the equation of minimal graphs, very classical, obtained by Lagrange at 1762, and says that if you have a piece of minimal graph, then you can write down this PDE, and this is very useful because you can then obtain representation formulas, explicit solutions, super solutions, sub-solutions, a priori estimates out of this PD. Second very important principle is the George's flatness implies smoothness principle that says that when you have an area minimizing surface which is very close to a plane, then it must be super smooth analytic actually. Third is Fleming's monotonicity and blow-ups and Federer's dimension reduction principle. And they have to do with zooming in our minimal surface, we zoom in and we see that its area in a unit ball decreases. And thanks to this property, we see that in the limit, when we zoom in around a point more and more and more, we obtain a conical surface in the limit. And this conical surface is called the tangent cone or blow up at that point. And the fact that it is conical is very useful because it reduces in one dimension the complexity of the problem. And this can be used in several ways, as we will see a bit. And fourth, in fourth place, the answer to the question. So the regularity of subfilms given by the theory of Taylor and Almgren that says that subfilms are smooth except on analytic curves of triple junctions or isolated quadruple junctions. And this is a bit in a picture, the result, this is Taylor, this is Almgren making some films and the paper of Taylor. And this is a picture that shows how in a subfilm, these singularities, their theory predicts already are there and are as they predict, right? So this is one topic, minimal surfaces on one hand, very classical topic. And let's go to another very classical topic that is the Stefan problem. So here we want to describe an ice-water interface, ice melting in water. And the questions are, is the interface between ice and water smooth? Is it possible that at some time it develops singularities? For instance, who knows a fractal structure? And how large can the singular set be? So we have this type of generic questions. So let's go to a more precise mathematical formulation. It's rather simple. We have a domain, omega in R3, that we can think as a water tank. And then there is a block of ice at 0 degree centigrade inside of the water tank. And the non-negative temperature on the boundary of the tank is prescribed. I will denote by theta the temperature. Theta equals to 0 on the ice, constant equal to 0. Theta is positive in the water. And then inside the water, of course, the temperature solves the heat equation. And on the interface, on the ice-water interface, we have this relation here that simply comes from differentiating the fact that theta is 0 here, but the free boundary is moving. And this connects the partial derivative with respect to time, the gradient, and the velocity of the free boundary. But on the other hand, since the velocity of the interface must be proportional to the heat absorbed by it, by Fourier's law, we get that the velocity is minus the gradient of theta, which we can plug here and close the equations. So this is, when we close this is the classical formulation of the Stefan problem. And now we go to a third problem, still disconnected. We will connect them later. The obstacle problem that consists of minimizing the Dirichlet energy, but with a restriction that is among functions that are above some given concave function phi, that is called the obstacle, and with prescribed boundary values. So this minimizer exists and has a so-called a context set where V is equal to phi, this set like sort of green here. And one can see that the Laplacian of V of the solution is non-negative, non-positive and supported on Z. And the difference U, that is V minus phi, minimizes this nice and convex function that I will call J obstacle and solve this PDE, that is the obstacle problem, where the Laplacian is equal to 1, where U is positive, U is non-negative everywhere, And here is the interesting condition. U on this boundary of the set U positive, U and the gradient of U must both vanish. And this boundary of the set U positive is what is called the free boundary, is also in some sense an unknown of the problem. So first connection between two problems, between the obstacle and the Stefan problem. This is from year, sorry. From 1973, let me try to, from 1973, sorry, let's go back again. Yes, connection between the obstacle and Stefan problem, 1973, and this is Duvaut transformation. So we take this local transformation, we consider the integral between T0 and T of the temperature theta that appeared in my slide of the Stefan problem. And this is a local transformation. We can do this inside of a very small cylinder inside of our water tank. So a very small ball in space and cylinder in space-time. And the new function solves what is called the parabolic obstacle problem. That is just a parabolic version of the obstacle problem we saw before. And actually this problem is the gradient flow, the L2 gradient flow of the convex functional that we saw before, that I call J obstacle. And this is the point of this transformation. The point of the Duvaut transformation is that you are unraveling some convex structure which was hidden and in the Stefan problem, and that is very, very useful for its mathematical analysis. But we have a second condition that we should not forget, is a strong monotonicity condition. This will appear at the end of my talk, is that the partial derivative with respect to time of U is strictly positive inside of the set where U is positive. This happens for every solution of the Stefan problem when you transform it in this way. And after the transformation, the ice just becomes the set where U is 0, the water is the set where U is positive, and the interface or free boundary is the boundary of the set U positive. Now, so this is the state of the art a bit in 1980. So shortly after this Duvaut transformation, a lot of progress happened on these problems. And the main breakthrough was this theorem, this theory of Caffarelli. And to describe it, you will see that blow-ups play a central role, a bit as in minimal surfaces. And here the natural zoom in for the problem is this, this scaling here. This scaling here is the way to rescale the solutions and zoom in around a point in a way that you always get, in some sense, that the equation becomes invariant under this scaling, this one here. And then Caffarelli theorem says that given a point in the ice-water interface, you are in one of the two situations. So either when you zoom in a lot, you see a situation where half of the space is ice and half of the space is water. And this is this type of blow up here. And in a neighborhood of this type of points, you see a very smooth analytic hypersurface moving smoothly. Or the alternative, or else, the blow up converges to a quadratic convex polynomial, and the ice at those points has a cuspidal singularity that can be imagined as follows. So the ice will get, as in here, will get thinner and thinner, then it arrives at a contact situation, and then it breaks into two pieces. 20 years after, we have more progress on the problem, and we see the first results on trying to understand singular points. So in 1991, Sakai gave this very precise description of singularities in the case of the elliptic problems, so no time, and only in 2 dimensions. But this description exhibits the complex analytic behavior, and also it gives you some flavor of the typical types of expansions such solutions will have. For instance, an example is here. I wanted to highlight here that so he can do an infinite order expansion, but the terms appearing here will have often fractional order, right? So it's a bit, it's a fractional expansion, and we will see a bit why a posteriori these kind of expansions hold with these fractions. So in 1998, Caffarelli revisited the problems and used for the first time a monotonicity formula. It's the first time that monotonicity formula was used for these problems, and he could prove this expansion, quadratic expansion at every singular point. That is, of course, much weaker than Sakai, because it's only quadratic plus little o of x squared. But at least it works in every dimension and also for the parabolic problem. And in 1999, Weiss introduced for the first time methods much more analogous to the theory of minimal surfaces. So he introduced this monotonicity of the energy, as in minimal surfaces, the energy now adjusted in this problem, but is monotone. And this gives homogeneous blow-ups, just as in minimal surfaces. And also he uses an epiperimetric inequality approach that is reminiscent to like the classical proofs of the principle that I described, the Giorgi flatness implies smoothness principle. So where were we at 2017? As a consequence of Caffarelli results, it was known that for every time slice, the singular part of the ice-water interface can be covered by hypersurfaces of class C1. This was a result from 2015, but is based on Caffarelli largely. But however, we could not rule out admittedly pathological situations, such as like solutions for which the singular piece of the free boundary could be as large as the smooth part of the free boundary for many, many times, or solutions with singular points in every time slice. So very pathological pictures that we should intuitively would like to rule out, but we don't know how. And it is not so easy to rule out. It cannot be so easy to rule out because we have these examples which are actually very easy to construct, in which we see that indeed the singular set can be as large as the regular part of the free boundary for many times, even countably many times. If you take an initial condition radial like this with different, this is the ice and everything is radial, then this will develop singularities at some times that we can choose a bit, and it can be countably many singular times. So positive results may be possible, but need to accommodate these examples that are not that nice. So before going, before seeing how we solve this, we need to introduce these minimal surfaces for the ambient or higher dimensional ambient that were in the title, these branching singularities and Almgren's theory. So maybe the story starts a bit about this minimal surface in dimension 4 or higher. Start a bit with this classical result of Wirtinger and Federer from the 70s that says that any holomorphic curve in R4, that is R4 is the same as C2 here, any holomorphic curve is area minimizing. So one example that will be useful to illustrate things later is this one. Is if you take x1 plus ix2 squared equals to x3 plus ix4 cubed, this is a holomorphic curve, and around the origin, so this is area minimizing by this result, and you see around the origin, if you plot x1, for instance, as a function of x3 and x4, you see this kind of self-intersection. And this is what is called the branching singularities, like a new type of singularities that does not appear for minimal surfaces in 3 dimensions, but yes, in higher dimensions. And in some sense, these singularities correspond, at least in explicit examples, to multiple valued complex functions like kth roots. And the difficulty of this type of singularities is that this de Giorgi principle of flatness implies smoothness fails at these singularities. So Almgren worked for a lot of years on a theory that is very complete on this type of branching singularities. And he proved, I cannot describe in more detail, but essentially that any area minimizing m-dimensional surface in zeta n manifold, where n is at least m plus 2, behaves essentially like a holomorphic curve, and the singularities are as rare as would happen in a holomorphic curve. This is a paper of 1,000 pages and a modern revisit of the same theory was recently given by very important works of Delellis and Spadaro. And I would like to highlight some of the ingredients in Almgren's theory, which will be important later, that are these multiple valued harmonic functions, the frequency formula. Now they are only titles, but we will see these titles appear again. So that's it's only titles, multiple valued harmonic function, frequency formula, and the concept of central manifold. So we have this. The last problem I would like to introduce is the thin obstacle problem very quickly. It's like the obstacle problem we saw before. So you minimize the Dirichlet energy, but now the restriction, the obstacle is only on a lower dimensional set, like a hyperplane here. So you minimize this Dirichlet energy with some boundary conditions, and you ask U to be non-negative only on xn equal to 0. See. And the type of solutions look like this. So this axis here would be xn, so in 2 dimensions, this would be x2 and x1. And then, so this would be xn equal to 0, and the solution will have a contact set here, and then it's positive on the rest of the, say, of the axis here in 2 dimensions. This is how the solutions of the thin obstacle problem look like, and we don't need to know much more about them by now. But but what I want to explain is a connection now between the thin obstacle problem and these branching singularities that we have seen. And this connection I like because it's very easy to visualize, and it is implicitly suggested by the work or by the techniques used in the work of Athanasopoulos, Caffarelli, and Salsa in 2006, where they proved a regularity theory for the thin obstacle problem using essentially the methods of Almgren. So the idea is that if you take a solution of the thin obstacle problem and you turn it upside down, you get 2 graphs. This is the same solution turned upside down, and you glue them together, you get this thing. And this is really, behaves exactly like a two-valued harmonic function. And in many analytic examples, is really a two-valued harmonic function, like the ones of Almgren. Like in these are like real graphs produced with so real plots. And this is really a solution of thin obstacle problem, and this is really a two-valued harmonic function, right? So here is there is a first connection that is not that far in some sense. And now, so to see how we made recent progress on the obstacle and on the Stefan problem, we need to introduce another connection that will make all of our paths connected. Now, what is missing is this connection here, is the connection between the thin obstacle problem and the obstacle problem. And this is a story that starts in this paper with Figalli in 2019, so published in 2019, but it starts in 2017. And what we do is we start, our starting point is Caffarelli. So we know this expansion at singular points, the quadratic expansion. And so Sakai tells us that in 2 dimensions, we should be able to continue this expansion. So it's natural to ask, is it also true in higher dimensions that we always have an X order in the expansion? And how do you find an X order in the expansion? So we can consider the solution around this point, so centered at this point, minus the quadratic polynomial, the second order expansion, and then try to divide by, try to zoom in and divide by some right quantity and get some limit, right? So the warning is that this, so typically like for harmonic functions, analytic functions, we just get powers of R here and we get the next order, or even for solution of Signorini or things like that. The warning is that here for the obstacle problem, in dimensions 3 or higher, this may not be true at every singular point. So it's not like this. You cannot just simply do this and get the next order like another power. But there is something that survives, and a very nice thing is that the Almgren frequency formula that I mentioned before, but now I write for the first time, is this expression here. This is monotonically increasing when you apply to the difference, to u at a singular point minus the quadratic polynomial. And using this fact, we can prove that accumulation points of this type of sequences, where you divide by the size of the function in the boundary of a ball, always exists. So you get accumulation points, and not only exist, but they are homogeneous. They are homogeneous, a bit like in minimal surfaces, they are cones, or also as happens in Almgren theory, right? And also they are solutions to some problems that we already saw, that they are solutions, either harmonic functions, which we control very well, or solutions of the thin obstacle problem. So this gives the connection. So when you subtract the quadratic polynomial and you blow up, you get solutions of the thin obstacle problem. However, and this is a warning we should have in mind, things are not easy. It may not be true that this number by which we divide is comparable to rk to the lambda. So the homogeneity is given by the value at 0 of this frequency formula, but it may not be true that this is comparable to r to the lambda, or that the lambda, the next order, is really has homogeneity greater than quadratic. It can stick to the quadratic, and then this is very bad type of singularity. But still, something positive survives, and what we can do is try to mimic the Almgren strategy using these dimension reduction principles, etc., in order to show that outside of a lower dimensional subset of the singular set, we can get more and more precise expansions. And this is easier said than done. And to implement this, of course, required a lot of work and a handful of new ideas, which were developed in 3 stages in the following 3 works, 2019, 2020, and this one. It's not our work. It's from 2 students here in Zurich, 2021, but it's very, very good piece of work, which I also recommend. So the theorem combining all of this work, or one of the theorems we can prove now, is that for every solution of the obstacle problem, the classical obstacle problem in the simplest setting, if you want, for simplicity, the following infinite expansion in homogeneous harmonic polynomials holds at singular points after you remove a set of dimension n-2. This is just an expansion where you get the Caffarelli, the first term, and then you get more and more harmonic polynomials, and this just means that you can go up to any order you like. So when you get, so what is the concept? So why are these precise expansions at most singular points useful? So what can we prove today which we couldn't in 2017? For instance, we can prove that outside of an n-2 dimensional set, the singular set, so removing some, let's say, garbage set, the singular set can be covered by smooth hypersurfaces of class infinity. Or a bit with an analogy with the Morse-Sard theorem, when we know higher order differentiability at singular points, this should improve our control on singular values. And with this type of heuristic, we could prove the following theorem, that is when you have a one parameter family, monotone family of solutions of the obstacle problem, then the singular set must be empty for almost every value of the parameter. So you have a parameter, for instance, the boundary values, you add some parameter to the boundary values, you can move it, the solution up, and but it's very general, you can do other things. And then for almost every value of the parameter in dimensions 2, 3, and 4, you will have no singular points at all. And in particular, this answered positively a conjecture of Schaeffer from 1974 in these dimensions 3 and 4. Okay, so now that we saw the connection and the implications of the with the thin obstacle problem and the obstacle problem, everything became connected. So we can say, why not to apply also these Almgren kind of methods to the Stefan problem, to the parabolic problem. And of course, you can try to do that. You can try to do that, and it makes sense. So we try to apply the same strategy to the parabolic obstacle problem. There is an equivalent of the frequency formula, that is the Poon frequency formula. There is a parabolic replacement for each elliptic thing in principle. And you can improve the Caffarelli expansion and obtain that at most singular points you go up to cubic order with a little o. But here we see something interesting, is that, remember that I told you that we have, for solution of the Stefan problem, we have this strong monotonicity. So by this strong monotonicity, in this cubic expansion, this coefficient here that goes in front of an absolute value of xn, see, this must be positive. At every point where you reach the cubic expansion, the coefficient is positive. And therefore, the cubic order in the expansion is never harmonic or caloric. So this means that we cannot treat simply this term as a curvature correction and use it to construct what is the analog of Almgren's center manifold. So this you treat as a curvature and then you discount the curvature and you continue. This cannot be done. This term has another meaning. And the elliptic and the parabolic problems completely diverge after cubic order. So they cannot be treated one a generalization of the other. So the statements will be completely different. We can go up to cubic order, but then we cannot go beyond with these methods. So we were, in some sense, after incorporating all of these, we were halfway of the journey still towards proving a really satisfying result for the Stefan problem, because the cubic expansion do not have all the, they had some new consequence, of course, but all the nice consequence which higher order expansions could potentially have. So a very critical step in our new paper, it's a recent print, is to enhance this cubic expansion. And it looks like technical, but it's not. There is I don't have much time to explain, but there is a deep reason why this is the critical step. So we want to go from this little o of cubic, let's say. Here I write this square root of t. This is like the parabolic scaling. And these are a square root of minus t because you obtain expansions for negative t. This is just to remind that the term is negative. So this is not an imaginary number or something. This is just the square root of the absolute value of t, but it only works in the past. So we had this expansion, and we want to put the same thing to the power 3 plus beta, so to gain a tiny power. And this is the main difficulty. So to do this, and to do this new step, we need to a completely new strategy, in some sense, a la Caffarelli. So not this diverges from Almgren. And this is based on barriers, scaling, parabolic estimates, what we call blow-ups with growth control, another type of blow-ups that do not use a monotonicity formula or are homogeneous or things like that. So this is a new strategy. And I would like to highlight that, to our knowledge, this is the first instance of dimension reduction type results, in some sense a la Federer Almgren, the type of consequence we obtain, but it does not rely on any monotonicity formula to giving homogeneous blow-ups. And here is in some sense, the main novelty of this strategy. And it's, of course, a bit of work to do that. And now, using this, what we can prove today on this Stefan problem is the following theorem. That is that for every local solution of this parabolic obstacle problem, that it's just a Stefan problem after Duvaut transformation, satisfying this strong monotonicity property, which is also satisfied in Stefan problem. The singular set has a subset sigma infinity with the following properties. I will make a picture now, just to end in 1 minute. So the singular set has a subset sigma infinity such that when you look at the spatial projection, it can be covered by C infinity n-1 dimensional manifolds, so codimension 1 manifolds in space. And when you look at the projection of this set on the time axis, it has dimension 0. And the interesting is that the rest of it is lower dimension in a very strong parabolic sense. So the complement of the singular set, the complement of sigma infinity inside the singular set is really lower dimensional, and hence like less important. So this is an illustration of what I mean by sigma infinity is a set that has a very small projection on the time axis, 0 dimensional. And when you project the project in the space, it's like the union of all of this curve, you project it down. You have something that can be covered by C infinity manifold, so very strong regularity in space. And also this is a bit sort of illustration, but maybe more difficult to explain, of what it means that the complement of sigma infinity has parabolic Hausdorff dimension n-2, which is stronger than saying that it has Hausdorff dimension n-2 in the space-time. It's a stronger notion is this parabolic dimension, but at this point is maybe a bit technical. So let me just end with these two new results, commenting on these two new results that are consequences of this theorem I described in my previous slide on the Stefan problem. So first result is that we now know that the set of singular the set of singular times, so the times at which you have at least one singular point for the physical Stefan problem. So physical, I just mean that in 3 spatial dimensions, because this is what you get in a block of ice. In this case, the set of singular times has dimension 1/2, and hence, in particular, it has measure 0, which was not known either. So it was not even known that it had measure 0, but we can prove a much stronger estimate, dimension 1/2. And also in 2 dimensions, sorry, here maybe it's I said physical, this is a cut and paste error, sorry. So the physical would be 3D, but the 2 dimensions in some sense is also physical with respect to some applications. But then the set of singular times we are in 1 dimension less, it's really 0 dimensional. So this is almost the best result one can obtain, because we have seen that in the examples, the set of singular times could be countable. So with respect to the measure theoretic point of view and 2-dimensional point of view, countable and 0 dimension is the same dimensional. So it's unlikely to improve this. And with this, I would like to end and thank you for your attention. Thanks.